What if the most important decision you ever made wasn't your own, not your choice of career, not your choice of partner, not even the choice to be born? What if the most consequential decision in your life, the one that sculpted your entire reality, was made by a single infinitesimal particle a billion years ago, in the heart of a star you've never seen? It's a disquieting thought suggesting our lives are not a grand narrative we write for ourselves, but the final settled verse of a story whose pivotal lines were written in the language of quantum mechanics long before we could ever read them. Every action you take, every thought that flickers through your mind rests upon a bedrock of cosmic history, a chain of cause and effect stretching back to the dawn of time. But physics, the very science that reveals this interconnectedness, also whispers a far stranger, more radical possibility. It suggests that the chain of causality isn't a single unbreakable tether to the past, but an endlessly branching tree of possibility, and that you are not living on just one of its branches. You are living on all of them all at once. To understand this staggering claim, we must abandon the world we know, the solid, dependable world of tables and chairs of definite outcomes and singular histories. We must journey down past the scale of molecules, past the atom, into a realm where the rules of reality seem to dissolve into a fever dream. This is the quantum world, and it is less a place of things and more a place of pure potential. Here, a particle like an electron doesn't simply exist at a single point in space. Instead, it exists everywhere it could possibly be, simultaneously a ghostly cloud of probability, a whisper of existence smeared across the void. It doesn't spin in one direction clockwise or counterclockwise like a tiny planetary top. It spins in all directions at once, a shimmering haze of contradictory states, holding within itself both up and down in a delicate, undefined superposition. This isn't a metaphor. It is the mathematical and experimental reality of the universe's fundamental building blocks. They are not concrete marbles of matter, but fluid symphonies of potential waiting for a reason to play a single definitive note. For nearly a century, we have witnessed this impossible duality with our own eyes. In the famous double-slit experiment, a cornerstone of modern physics, we can fire a single photon, a lone particle of light, towards a barrier with two narrow openings. If we aren't looking, if we allow it to travel unobserved, this solitary photon behaves not as a particle at all, but as an ethereal wave. It somehow passes through both slits at the same time, interfering with its own phantom self on the other side, creating a pattern of light and shadow that could only be produced by a wave washing against a shore. A single entity in two places at once. But the moment we try to catch it in the act, the moment we place a detector at the slits to ask, "Which path did you take?" the game changes entirely. The ghostly wave vanishes. The photon, as if suddenly shy under our gaze, snaps to attention and behaves like a respectable solid particle. It picks a single slit, travels through it, and strikes the screen behind as a single, unambiguous point of light. The very act of measuring it, of asking a question, seems to force the universe to abandon its ambiguity and make a choice. This is the deepest, most persistent mystery in all of science, a profound schism that cuts right through the heart of physics. It's called the measurement problem. How does the blurry, probabilistic, many states at once world of the quantum realm transform into the sharp, certain one state, only reality we experience every single moment? What happens to all those other possibilities? When the electron that was spinning both up and down is measured and we find it spinning up, where did the down possibility go? Did it simply vanish from existence? Was it erased from the cosmic ledger as if it had never been a potential reality? For decades, the prevailing view, known as the Copenhagen interpretation, proposed just that. It stated that the act of observation mysteriously and inexplicably collapses the wave function, forcing one single outcome to become real while all other potentials are annihilated. It was a functional, if deeply unsatisfying answer. It treated the observer you as a classical entity with an almost magical power to crystallize reality from the quantum fog without ever explaining the mechanism behind this cosmic sleight of hand. The equations of quantum mechanics, which so beautifully describe the evolution of the wave of possibility, simply fell silent at the moment of collapse, offering no clue as to how or why one future is chosen over countless others. It left a gaping wound in our understanding of the universe, a point where our most fundamental theory simply shrugs and says it just happens. But in the 1,950 seconds, a brilliant and audacious graduate student at Princeton named Hugh Everett III looked at this problem and proposed a solution so radical, so profoundly unsettling, that it was dismissed by his peers for decades. He looked at the pristine, elegant mathematics of quantum theory, the Schrödinger equation, which describes how quantum systems evolve over time, and he noticed something remarkable. The equation never not once predicted any kind of collapse. It described a universe that evolved smoothly, perfectly, with all possibilities always remaining intact. The collapse was not in the math. It was a rule that physicists had bolted on afterwards to make the theory match our singular experience. Everett asked a breathtakingly simple yet revolutionary question. What if the math is right? What if there is no collapse? What if the universe doesn't in fact ever choose? The implication of his question is an abyss of possibility. If the wave function never collapses, then when you measure that electron spinning in a state of both up and down, both outcomes must still exist. The up result doesn't erase the down result. Instead, in that infinitesimal sliver of a moment, reality itself cleaves in two. The entire universe fractures. In one universe, you, the observer, measure the electron spinning up. Your brain registers it, your pen records it in a notebook, and your history from that point forward is the history of someone who saw up, but in another perfectly real universe. A universe that splits off from your own at the instant of measurement. A duplicate of you sees the electron spinning down. That version of you, equally real, equally conscious, records down in their notebook and proceeds into a future consistent with that outcome. The river of time didn't just flow onward. It bifurcated into two parallel streams, each one as real as the other. All the potential contained within that quantum wave of possibility was conserved not by vanishing, but by creating a new stage, a new cosmos for each outcome to play out upon. This is the many worlds interpretation, and its consequences are almost too vast for the human mind to contain. It suggests that every single quantum event, everywhere in the cosmos, at every moment in time, is causing the universe to branch. Not just in a laboratory, a stray particle of cosmic radiation striking a molecule in the Earth's atmosphere, with a 50/50 chance of interacting or passing through, the universe splits. A radioactive atom in the granite of a mountain, its decay uncertain. The universe splits. The chemical reactions firing across the synapses in your own brain, the tiny quantum leaps of electrons that underpin every single thought, every decision, every hesitation. Every one of them is a branching point. There is a universe where you took that job, another where you turned it down. A universe where you caught the green light, and another infinitesimally different where you were stopped by the red. There is a version of you who is a hero, a villain, a success, a failure, a version who lived, and a version who died. Every path not taken in your life was in fact taken by another you, in another world, born from the quantum fabric of that moment of choice. Suddenly you are not a single individual navigating one life. You are an infinite collection of individuals, a sprawling, ever-growing family tree of selves spread across a multiverse of staggering, perhaps infinite complexity. The person you are, the memories you hold, are merely the story of one specific path through this boundless garden of forking paths. You feel unique, singular, because your consciousness is confined to a single branch. You cannot perceive your other selves, just as a person standing on a riverbank cannot experience the journey of a boat that has drifted down a different channel. Yet according to this theory, they are out there, an uncountable number of you living out the consequences of every quantum coin flip that has ever occurred. They share your past, your DNA, your memories right up until the moment of divergence. They are you in every sense of the word. Are you the original? The question itself may be meaningless. Each branch is as real, as fundamental as the next. This is not science fiction. It is a serious, literal interpretation of our most successful scientific theory, one that is gaining more and more traction among physicists who are tired of the philosophical baggage of collapse. It resolves the measurement problem with a breathtaking elegance, preserving the integrity of the mathematical laws that govern reality. But it does so at a terrifying cost to our sense of self. It forces us to confront the most profound questions of identity and existence. If there are infinite versions of you, what does it mean to be times you times? Is your consciousness merely a temporary pattern on one branch of an infinite cosmic tree? Where are these other worlds? Are they layered on top of our own, separated by a thin quantum veil? Or are they unimaginably distant, forever beyond our reach? And what does this mean for free will, for morality? For the significance of a single life in a cosmos that contains all possible lives? The many worlds interpretation doesn't just offer an answer to a puzzle in physics. It presents a vision of reality that challenges the very foundations of what we believe ourselves to be. And as we venture deeper into its strange and beautiful logic, we may find that the universe is not only stranger than we imagine, it is stranger than we can times imagine. The story of you is not one story, it is all of them. What if the world you experience, the life you are living, is only one page in a book of infinite pages, not a metaphor but a physical truth? What if every choice you've ever made, every path you didn't take, branched off to create a new universe, a new you, living out that alternate reality? This isn't the fanciful dream of science fiction. It is the startling, logical, and terrifying conclusion of our most successful scientific theory, a theory born from a crisis that shattered our very understanding of existence itself. Our story begins not with answers, but with a profound and unsettling question. It begins at the moment when our map of the universe, so elegantly drawn by centuries of genius, suddenly led us to the edge of a cliff, revealing a chasm of impossibility that defied all logic, all reason, all common sense. For generations we thought we had it solved. The universe we believed was a magnificent and predictable machine, a grand cosmic clockwork set in motion at the beginning of time and ticking along according to immutable discoverable laws. Isaac Newton had given us the blueprint in the 17th century. His laws of motion and gravity were more than just equations. They were a philosophical statement. They described a world of certainty. A world where if you knew the precise position and momentum of every particle in the universe, you could in principle calculate the entire future and retroactively discover the entire past. This deterministic dream reached its zenith in the mind of the French mathematician Pierre-Simon Laplace. He imagined a vast intellect, a demon he called it, that could comprehend all the forces of nature and the state of every atom. For such an intellect, he wrote, nothing would be uncertain. The future, just like the past, would be present before its eyes. This was the bedrock of classical physics, a universe of cause and effect of solid objects in definite places moving on predictable paths. A baseball, a planet, a star, they all played by the same reliable rules. Reality was solid. It was intuitive. It was, for lack of a better word, time's real asterisk. But as the 19th century gave way to the 20th, strange cracks began to appear in this perfect clockwork facade. Experiments in laboratories across Europe started to yield results that were not just unexpected, but utterly nonsensical. Physicists studying the nature of heat and light found themselves staring into an abyss. Their theories predicted that a simple hot object should radiate an infinite amount of energy, instantly sterilizing the universe in a flash of ultraviolet light, an outcome they grimly nicknamed the ultraviolet catastrophe. Since reality had stubbornly refused to catastrophically end, their understanding of reality was clearly fundamentally broken. The first tremor of the coming earthquake was felt in the year 1900. A quiet, meticulous German physicist named Max Planck, in what he later called an act of desperation, proposed a radical, almost heretical idea. He suggested that energy was not a smooth, continuous flow like water from a tap. Instead, he argued, it could only be emitted or absorbed in tiny, discrete packets like individual drops. He called these packets quanta. Imagine walking up a ramp versus climbing a set of stairs. Classical physics saw the world as a smooth ramp where you could occupy any height you wished. Planck was saying that nature at its most fundamental level was a staircase. You could be on one step or the next step up, but never in between. It was a bizarre ad hoc solution designed to fix a mathematical problem, and even Planck himself was deeply uncomfortable with its implications. He had hoped it was merely a computational trick, a temporary scaffold that would be replaced by a more sensible classical explanation. He had no idea he had just pried open a Pandora's box. He had just laid the foundation stone for quantum mechanics. What followed was one of the most intellectually violent and creatively fertile periods in the history of human thought. The old world was being torn apart by war and revolution, and in the quiet halls of universities, the old universe was meeting a similar fate. A new generation of physicists, a veritable pantheon of titans, assembled to chart this strange new territory. There was the Danish master Niels Bohr, a philosophical patriarch whose Copenhagen Institute became the global epicenter of this new physics. Bohr spoke in riddles and paradoxes, believing that the weirdness of the quantum world was a fundamental truth we simply had to accept. Then came the young German prodigy Werner Heisenberg, a firebrand of breathtaking genius. He was ready to throw out all the old pictures of reality atoms as tiny solar systems, electrons as tiny balls, and replace them with pure abstract mathematics. And there was the Austrian Erwin Schrödinger, an elegant aristocratic intellectual who more than anyone else would provide the beautiful mathematical language to describe this new world, even as he recoiled in horror from its bizarre, philosophical consequences. Together, through years of ferocious debate, collaboration and rivalry, these minds forged an interpretation of the quantum world that would become the reigning orthodoxy for a century. It is known as the Copenhagen interpretation, and it is responsible for the modern world. The laser in your Blu-ray player, the transistor in your smartphone, the nuclear power that lights our cities, all are children of this theory. It is the most powerful and precisely predictive theory ever devised by humanity, and it is by the standards of everyday logic completely insane. The Copenhagen interpretation tells us something profoundly unsettling about the nature of reality before we look at it. It says that a fundamental particle like an electron does not have a definite position or a definite speed until it is measured. Before we observe it, it exists in a ghostly state of pure potential, a condition we call a superposition. Imagine a spinning coin just before it lands. Is it heads or tails? The question is meaningless. It is in a sense both and neither. The electron before observation is not just in one place. It is in a cloud of all possible places at once. It is not just moving at one speed. It is moving at a smear of all possible speeds. Its existence is described not by a single solid number, but by a wave function, a mathematical object discovered by Schrödinger that represents this shimmering, ethereal ghost of possibility. This wave isn't made of water or sound. It's a wave of probability. Where the wave is high, the particle is likely to be found. Where the wave is low, it is unlikely. But until you look, it is everywhere and nowhere. It is a haze of what could be. This alone is strange enough to challenge our deepest intuitions. But the true madness lies in what happens next. The instant you perform a measurement, the instant you look, the instant you interact with the particle to find out where it is, something dramatic, almost magical occurs. The entire wave of possibility, which may have been spread out over vast distances, instantaneously collapses. The shimmering ghost vanishes. The superposition is shattered. And out of that infinite menu of possibilities, one single, definite reality crystallizes. The particle clicks into place, appearing at one specific location, as if it had been there all along. The universe, it seems, has made a choice. This is the infamous wave function collapse. It is the central pillar of the Copenhagen interpretation, and it is also its deepest, darkest mystery. For nearly a century we have wrestled with this moment of collapse. It marks the violent transition from the indefinite, ghostly quantum world of potential to our definite, concrete, classical world of experience. Bohr and Heisenberg argued that we shouldn't even try to visualize what's happening. The quantum realm, they insisted, is fundamentally unknowable. Asking what an electron was doing before we measured it was, in their view, like asking what the sound of one hand clapping is. The question itself was meaningless. The math worked. The predictions were flawless. We should, in their famous mantra, just shut up and calculate. The job of physics, they argued, was not to describe what nature times is times, but but only to describe what we can times say, times about nature through our experiments. This instrumentalist view was profoundly unsatisfying to many, including some of the theory's own architects. It felt less like a scientific explanation and more like a philosophical surrender. It was as if reality was a stage play, and we were forbidden from ever looking behind the curtain. The actors only put on their costumes and took their positions the very instant we, the audience, turned to look at them. What were they before? The theory offered no answer. It just told us not to ask. Albert Einstein famously detested this idea, protesting that God does not play dice with the universe. He believed that quantum mechanics was incomplete, that there had to be some hidden underlying reality, some clockwork we just hadn't discovered yet, that was determining the outcomes we perceived as random. But it was Erwin Schrödinger who articulated the problem most devastatingly. He was horrified by the central role the observer seemed to play in creating reality. He saw this jump from a ghostly superposition to a single concrete state as a grotesque mockery of logic. To expose what he saw as the sheer absurdity of the Copenhagen interpretation, he devised a thought experiment, a diabolical piece of scientific satire so brilliant and so disturbing that it has haunted physics ever since. It is a story you have likely heard. It is the story of Schrödinger's cat. Imagine, Schrödinger said, a sealed steel box completely shielded from the outside world. Inside this grim container, we place a cat. Along with the cat, we place a device of fiendish design. It consists of a single radioactive atom, a substance so unstable that within 1 hour, there is an exactly 50/50 chance that it will decay. The state of this atom is purely quantum. Until it is observed, it exists in a superposition of both states. It has both decayed and not decayed simultaneously. Now we link this quantum event to our everyday macroscopic world. We rig the device so that if the atom decays, it triggers a Geiger counter. The Geiger counter in turn is connected to a small hammer. The hammer is poised to strike and shatter a glass vial containing a deadly poison, hydrocyanic acid. If the atom decays, the hammer falls, the vial shatters, the poison is released, and the cat dies. If the atom does not decay, the hammer does not fall, and the cat remains alive. We seal the box, and we wait for 1 hour. Now we must ask ourselves the crucial question before we open the box and look inside: what is the state of the cat? According to the rigid laws of the Copenhagen interpretation, the answer is inescapable and monstrous. The atom inside the box, being unobserved, remains in its superposition of decayed and not decayed. Because the cat's fate is inextricably linked to the atom, because the entire system is one interconnected quantum state, the cat itself must also be in a superposition. It is not that we simply don't know whether the cat is alive or dead. The theory dictates that the cat is literally and physically both alive times and times dead. It is a zombie and a living creature intertwined, a grotesque fusion of mutually exclusive realities trapped within that box. Its wave function contains both the living cat and the dead cat, each with equal reality. Only when we, the observer, open the box to check on it, does the wave function of the entire system collapse. Only then does the universe choose a single outcome. In that instant, the cat resolves into being either definitively alive, purring and well, or definitively dead, a tragic victim of quantum chance. Schrödinger did not believe this was actually happening, of course. He designed the experiment precisely because its conclusion was so obviously preposterous. A cat cannot be alive and dead. He was using it as a weapon, a times reductio ad absurdum times aimed squarely at the heart of the Copenhagen school. His point was this: if your theory leads to the conclusion that a cat can be in a state of living-dead suspension, then your theory has a very serious problem. He was trying to force his colleagues to confront the sheer lunacy that their equations seemed to imply when scaled up from the world of atoms to the world of cats, and by extension to the world of human beings and planets. He was illustrating the chasm at the center of their physics. He was pointing directly at the measurement problem. And here, in this chasm between the ghostly potential of the quantum world and the solid certainty of our own lies, the raw beating heart of the measurement problem, the central unresolved mystery of quantum mechanics, it is a nest of impossibly difficult questions. What precisely constitutes a measurement or an observation? What is the special process that causes the wave function to collapse? Is it the interaction with a large, complex device like a Geiger counter? Does it require the intervention of a higher, conscious mind, a human or animal observer, to register result? If so, does this mean that consciousness itself creates reality? This was an idea so troubling that it drove many physicists to distraction. Where do you draw the line, the so-called Heisenberg cut, between the quantum system being measured and the classical system doing the measuring? After all, the measuring device itself, and indeed the physicist opening the box, are all made of atoms. They too should obey the laws of quantum mechanics. So why don't we ever experience ourselves in a state of superposition, of having seen a live cat, times and times a dead cat? The Copenhagen interpretation offers no real answer. It simply posits the collapse as a fundamental unexplained rule. It declares that there are two different sets of laws for the universe. One, the elegant wave-like evolution described by Schrödinger's equation, governs everything so long as it is unobserved. The other, the violent, unpredictable collapse, takes over the moment an observation occurs. But it never explains how or why the universe switches between these two processes. It feels like a fudge. It feels like a magical incantation papering over a gaping hole in our understanding. It worked, it gave us the right answers, it allowed us to build the modern technological world, but it left us with a picture of reality that was fractured, inconsistent, and deeply, profoundly weird. For decades, this was the uneasy piece. Physicists learned to stop worrying and love the quantum bomb. They accepted the paradox of the cat, the mystery of the collapse, as a fundamental feature of the world, a quirk of nature we were not meant to understand any further. They built their careers and our future on a theory that told them reality was one way when you weren't looking and another way entirely when you were. The map of the universe was now split in two, with a strange, dark borderland where the rules mysteriously changed. But what if the Copenhagen interpretation, for all its power, was not the final word? What if the collapse of the wave function wasn't a real physical event at all? What if it was just an illusion? What if the universe never chooses one outcome? What if, in that dark and silent box, the moment the atom entered its superposition, reality itself cleaved in two, creating one universe where the atom decayed and the cat died, and another, equally real universe, where the atom remained intact and the cat lived? A universe for every possibility. What if the act of opening the box doesn't create one reality but merely reveals which branch of this endlessly multiplying reality you happen to find yourself in? This was a thought too monstrous, too fantastic for the founders to contemplate. But it was a seed that, once planted, would eventually grow into the single most staggering and reality-altering idea in the history of science. An idea that would suggest that the cat is in fact both alive and dead, just not in the same universe. And so the paradox remained a ghost haunting the elegant halls of physics. A schism cut through the heart of our understanding, a jagged line drawn between two irreconcilable realities. On one side, the smooth, predictable, and deterministic universe described by Erwin Schrödinger's beautiful wave equation, where possibility flows like a majestic, unbroken river. On the other, the chaotic, probabilistic, and jarring world of measurement, where that river of infinite potential inexplicably shatters into a single concrete outcome the moment we dare to look. This was the measurement problem, the skeleton in quantum mechanics' closet. The Copenhagen interpretation, championed by the formidable Niels Bohr, offered not a solution but a decree. It told us to stop asking what was happening behind the curtain. It posited a mysterious and ill-defined collapse of the wave function, an event triggered by the act of observation itself, which magically forced reality to make a choice. But for some, this was profoundly unsatisfying. It felt less like a law of nature and more like an admission of defeat. It elevated the observer to a near mystical status, a classical entity with the power to reach into the quantum realm and force its fluid nature into a solid state. The universe, it seemed, was split in two, a quantum world of ghosts and a classical world of observers who could exercise them. How could this be? Where was this dividing line? Is a cat an observer, a camera, a single bacterium? The theory offered no clear answers, only a persistent and troubling silence. physics was left with a masterpiece of predictive power that was built upon a foundation of philosophical quicksand. The question lingered whispered in the corridors of universities worldwide. What if the collapse isn't real? What if our theories aren't incomplete but our vision is too narrow? What if the problem isn't with the wave function but with us? Into this intellectual deadlock walked a young, audacious mind, a graduate student at Princeton University in the mid-1952s, a place where the ghosts of Einstein and von Neumann still roamed and the dogma of the Copenhagen school reigned supreme. His name was Hugh Everett III. He was not just a physicist, he was a logician, a military analyst, a man who craved consistency and recoiled from arbitrary lines drawn in the sand. He looked at the Schrödinger equation, this pristine mathematical jewel that described the evolution of quantum systems with flawless precision, and he saw its absolute uncompromised truth. Then he looked at the messy ad hoc concept of wave function collapse, and he saw an unnecessary scar upon that perfection, an appendage grafted onto the theory simply to make it fit our limited classical intuitions about a single definite reality. Everett asked a question so simple it was revolutionary, so radical it was considered by many to be scientific heresy. He asked, what if we just take the math at its word? What if we trust the Schrödinger equation, and only the Schrödinger equation to be the complete and total story of the universe? What if he dared to propose the wave function never collapses at all? It was a thought of breathtaking audacity to throw away the foundational crutch of quantum mechanics. The very mechanism that connected its strange probabilities to our solid world seemed like an act of intellectual insanity. Without the collapse, how could you ever explain the simple fact that when you look for an electron, you find it in only one place? How could you explain that when you open Schrödinger's infamous box, the cat is definitively alive or definitively dead? Never. Both Everett's answer contained within his 1957 PhD thesis, a document that would be ignored for over a decade, did not resolve the paradox by simplifying it. Instead, it expanded our very concept of reality to a scale so vast, so unimaginable, that it dwarfed all of creation that came before it. His solution was this: when a measurement is made, reality doesn't choose. Everything that times can times happen, times does times happen. The wave function in Everett's view is not merely a catalogue of possibilities. It is the blueprint for all of reality in its totality. The universe we inhabit is not a single solitary timeline, but an infinitely branching structure, a cosmic tree of staggering complexity. Let us return to that tormented cat sealed in its prison of quantum uncertainty. Before the box is opened, its wave function exists as a perfect superposition. The state of living cat coexists with the state of dead cat. The Copenhagen interpretation says that upon your observation, this delicate superposition shatters and one outcome is randomly selected. The other possibility simply vanishes from existence, an aborted timeline. Everett's logic follows a far more elegant, if terrifying, path. He says that at the moment of measurement, the universe itself cleaves. It splits into two distinct parallel branches. In one branch of reality, you, the observer, open the box and become part of a world where the cat has survived. You feel the relief, you hear the meow, you live out your life in a universe where the atom did not decay. But in another equally real branch, a perfect copy of you, indistinguishable from the person you believe yourself to be, opens an identical box and finds the cat has perished. That version of you feels the sorrow, registers the silence, and continues their life in a universe where the atom did decay. There is no collapse, there is no magical choice. There is only a splitting, a branching of the universal wave function. Every potential outcome encoded in the mathematics is realized. Each one is given its own stage, its own universe to play out. The version of you in the alive cat world has no knowledge of your twin in the dead cat world, and vice versa. From your perspective inside your own branch, it times looks times like a collapse. It times feels times as though reality has settled on a single outcome, because your consciousness is now inextricably tied to that outcome. You have followed one path on the branching tree and the other paths have become inaccessible to you. But they are not gone. They are just as real as your own. This process isn't reserved for dramatic life or death experiments. It is happening constantly everywhere on a scale that defies comprehension. Every quantum event, every particle interaction with multiple possible outcomes is a branching point for the cosmos. A photon striking a leaf, deciding whether to be absorbed or reflected, the universe splits. A cosmic ray zipping through your body with a probability of striking a cell's DNA. The universe splits. The countless ceaseless quantum jitters occurring in every cubic centimeter of space, every fraction of a second, are continuously splitting our reality into an exponentially growing web of parallel worlds. There is a version of you that turned left this morning instead of right. A version of you who took that job you turned down. A version that said the thing you wish you had said, and a version that held their tongue. Every quantum fluctuation that rippled through the neurons in your brain as you made a decision, however small, may have spawned a new timeline where a different version of you made a different choice. We are not sailing on a single river of time. We are adrift on one current in an infinite cosmic delta, a multiverse of branching streams, each representing a complete, self-contained, and entirely real universe. This is the core of Everett's theory of the universal wave function, what would later be called the many worlds interpretation. It is a proposal of breathtaking economy and grandeur. It removes the arbitrary division between observer and observed. It eliminates the need for a mysterious non-physical collapse. It posits only one thing, the universal wave function, and one rule, the Schrödinger equation, that governs its evolution. The price for this mathematical purity, however, is a dizzying, almost terrifying inflation of reality itself. We are forced to accept the existence of a near infinity of parallel Earths, parallel galaxies, and parallel selves, each one unaware of the others. But this raises an immediate critical question. If these other worlds are real, why can't we see them? Why don't we feel ourselves splitting? If another universe is created every time a particle interacts, why doesn't the world dissolve into a blurry, superimposed mess? The answer is the final, crucial piece of Everett's puzzle, a concept that would be refined for decades after him: decoherence. Decoherence is not a new force or a mystical process. It is the natural, inevitable, and astonishingly rapid consequence of a quantum system interacting with its environment. Imagine a tiny, perfect quantum system like our radioactive atom. Its wave function is in a clean superposition, a state of pure potential. We can call this a coherent state. Think of it like a single pure note played by a violin in a perfectly silent, soundproofed room. Its waveform is pristine, predictable, and self-contained. Now, what happens when we open the door to that room? The sound of the violin instantly spills out and interacts with the chaotic environment of the outside world. It bounces off walls, gets absorbed by curtains, interferes with the chatter of people, the hum of air conditioning, the rumble of traffic. The pure note's information isn't destroyed, but it becomes hopelessly and irreversibly entangled with the trillions of other sound waves in the environment. Its beautiful, simple coherence is lost to the noise. It has times decohered asterisk. This is precisely what happens at a quantum measurement. The moment the state of the atom, decayed or not decayed, interacts with even a single particle of its environment, like the Geiger counter, a catastrophic chain reaction of entanglement begins. The state of the Geiger counter then interacts with the air molecules around it, with the photons of light bouncing off of it with the mechanism of the hammer. The hammer's state entangles with the vial of poison. The poison's state entangles with the cat. The state of the cat, its very life or death, entangles with the flood of photons and air molecules filling the box. This information about the superposition, the both at once-ness, leaks out into the environment at nearly the speed of light. The alive cat state becomes entangled with a version of the environment that is consistent with a living cat. Simultaneously, the dead cat state becomes entangled with a version of the environment consistent with a dead cat. These two entangled systems, alive, cat plus its environment, and dead cat plus its environment, have their wave functions spread out across trillions upon trillions of particles. They quickly become so different from one another, so orthogonal in the vast mathematical space of all possibilities, that they can no longer interact. They can no longer interfere with one another. For all practical purposes, they have become separate worlds. Decoherence is the celestial chisel that cleaves one reality into two. It's the mechanism that ensures the branches of the universal wave function, once they split, cannot grow back together. It explains why you don't feel the split. Because you are part of the environment. The moment you open the box, the photons streaming from the cat and into your eyes entangle your own quantum state with its state. The electrochemical signals in your optic nerve, the pattern of neurons firing in your brain, your very consciousness becomes part of the system. One version of your brain becomes entangled with the living cat. Another version of your brain becomes entangled with the dead one. These two versions of you now inhabit causally isolated branches of reality. You don't perceive the other worlds because you are physically incapable of it. The information required to do so has been smeared across an impossibly vast and complex environment, lost like a whisper in a hurricane. The collapse of the wave function, then, is an illusion. A magnificent, pervasive, and deeply convincing illusion, born from the perspective of a single observer trapped within a single branch. What we experience as a random probabilistic choice made by the universe is, in Everett's view, merely our own consciousness following one path and losing all contact with the infinite other paths that were just created. This was the profound shift in perspective Everett offered. He took the observer down from their pedestal. We are not special classical beings who stand outside of quantum mechanics poking it to see what happens. We are quantum systems ourselves. We are intricate walking, thinking collections of particles, and we are subject to the exact same laws as everything else. When we observe the universe also observes us. When we measure a quantum system, we do not force it to collapse. Instead, we become entangled with it, and we are swept along for the ride as the river of reality forks. There is no split between the quantum and classical worlds, because there is no classical world. There is only the quantum world appearing classical from our limited viewpoint within it. Everett's thesis, elegantly titled The Theory of the Universal Wave Function, was a complete self-contained cosmology in miniature. It presented a universe that was vastly larger and stranger than ever imagined, yet governed by a single beautifully simple mathematical law. It replaced the troubling randomness of collapse with the deterministic, if-branching evolution of a single, all-encompassing reality. But this vision, for all its logical purity, was deeply unsettling. It suggested that our unique identity is a fiction, that countless versions of ourselves, our loved ones, our entire history, are being spun off into existence with every passing moment. It implied that all outcomes, the triumphant and the tragic, are played out somewhere in this grand cosmic tapestry. Somewhere, a version of humanity avoided its worst mistakes, and somewhere else, a version made them even sooner. For a young student to propose such a thing in the 1,950 seconds, to quietly suggest that the entire Copenhagen school, led by the revered Niels Bohr, was fundamentally mistaken, was an act of supreme intellectual courage. He had taken their greatest paradox and declared it was not a paradox at all, but a glimpse into the true majestic and pluralistic nature of existence. His work was submitted, defended, and then largely it was buried. The physics community, for the most part, was not ready. The idea was too bizarre, too extravagant, too untestable. It reeked of science fiction. Everett's elegant solution to the measurement problem was a seed planted in a frozen, unreceptive soil. It would take a new generation of physicists decades later to unearth his work and recognize the profound beauty and power hidden within its audacious claims. The journey of the many worlds interpretation was only just beginning, and its first steps were into a long, cold wilderness of obscurity. The story of how this radical idea survived and was eventually reborn is a testament to the relentless human quest to understand the deepest and most fundamental question of all. What is the nature of the reality we call our own? And so, with a breathtakingly simple, almost defiant stroke of mathematical logic, Hugh Everett III had offered a way out of the quantum labyrinth. He had dared to take the Schrödinger equation at its word, erasing the arbitrary line between the quantum and the classical, and in doing so had seemingly healed the schizophrenic heart of physics. The universe, in his radical vision, never chooses. It simply accommodates all possibilities. You would expect such a profound revelation, a theory that claimed to solve the very measurement problem that had haunted the giants of science for decades, to be met with a storm of debate, of excitement, of furious intellectual engagement. Instead, the response that echoed back from the highest echelons of the physics community was not a storm but a vacuum, a profound, bone-chilling and utterly deafening silence. To understand this cold reception, you have to picture the world Everett had just walked into. The mid-1950s was the undisputed kingdom of Niels Bohr and his Copenhagen interpretation. It was more than just a theory. It was an orthodoxy, a creed forged in the fires of intense debate and solidified by the towering intellectual authority of its creator. Bohr was the patriarch of quantum mechanics, a figure whose pronouncements carried the weight of scripture. His institute in Copenhagen was the Vatican of physics, and he was its infallible pope. The dogma he preached was one of fundamental uncertainty and the indispensable role of the observer. The act of measurement in this view was a sacred and almost mystical event that forced reality to make a choice. Into this deeply entrenched establishment came Everett, a young, unknown graduate student from America, with an idea that wasn't just a critique but an act of heresy. His theory didn't just question the Copenhagen interpretation. It rendered its central mystery, the collapse of the wave function, entirely obsolete. It suggested that the high priests were performing a ritual that had no real power because the universe didn't need their intervention to make up its mind. It was a direct challenge to Bohr's authority, and it was not taken lightly. In 1959, Everett was given a chance to make his case, traveling to Copenhagen to meet the great man himself. We can only imagine the scene, the confident young theorist armed with the clean power of his equations, facing the seasoned philosopher king of physics, a man who had wrestled with the likes of Einstein and won. The meeting was a catastrophe. Bohr, deeply committed to his principle of complementarity and the irreducible role of the classical observer, was utterly unmoved. He saw no problem to be solved. He saw only the misguided ramblings of a student who had failed to grasp the subtle wisdom of the Copenhagen school. Everett's ideas were dismissed not with vigorous debate but with a kind of weary, paternalistic condescension. The message was clear: this was not the way forward. The doors of the temple were closed to him. The rejection was so complete, so absolute, that it broke something in Everett. He had offered the world a glimpse of a staggering, magnificent new cosmos, and the world had politely but firmly looked away, disillusioned and seeing no future for his ideas. In a field dominated by a single, unyielding perspective, Hugh Everett III did something almost unthinkable for a mind of his caliber. He walked away from it all. He finished his PhD. But his original sprawling thesis was brutally condensed at his supervisor's insistence, stripped of its most revolutionary language, and published as a short, obscure paper in a 1957 issue of Times. Reviews of Modern Physics *, buried alongside a supportive but ultimately dismissive commentary by his supervisor John Wheeler, who tried to reconcile it with the Copenhagen view. After this quiet, ignominious debut, Everett left the hallowed halls of academia for good. He turned his formidable intellect to the Cold War, applying his mathematical prowess to weapons systems analysis and operations research for the Pentagon. The man who had conceived of infinite universes now calculated nuclear fallout patterns. His grand theory, which should have ignited a revolution, became little more than a whisper, a curious footnote in the history of science, filed away and forgotten. For more than a decade, the many worlds interpretation languished in this theoretical desert. It was an idea stranded in intellectual exile, too strange for the mainstream, and too radical for a generation of physicists focused on the practical applications of quantum theory. The very thing that gave the theory its power, its sheer ontological extravagance, was also what made it so easy to dismiss. Infinite, unobservable universes. It sounded less like serious science and more like the fever dream of a science fiction writer. It seemed to violate the principle of Occam's razor, the idea that the simplest explanation is usually the best one. Surely physicists argued a theory that requires a single mysterious wave function collapse is simpler than one that demands the creation of trillions upon trillions of new universes every single second. It felt philosophically monstrous, a grotesque overpopulation of realities that could never be seen or tested. The scientific community, by and large, decided it was a price too high to pay for mathematical elegance. The Copenhagen view, with all its strangeness and its arbitrary division of the world, was at least conservative. It kept reality manageable. It kept times us, times at the center, our observations shaping the world. Everett's vision was a far colder comfort, a cosmos indifferent to our presence, branching endlessly with or without our consent. And there, in the dustbin of discarded ideas, the story might have ended. A tragic tale of a brilliant insight born before its time, a revolutionary vision that faded into obscurity with its creator. But an idea this powerful, this fundamental, is like a deeply buried seed. It can lie dormant for years, waiting for the right conditions for a mind brave enough to see the forest it promises. That mind belonged to a physicist named Bryce DeWitt. DeWitt was a distinguished physicist, a leading authority on general relativity and quantum field theory. In the late 1960s, he stumbled upon Everett's work. His initial reaction was the same as almost everyone else's: shock and disbelief. He famously wrote that he still recalled vividly the shock I experienced on first encountering this multi-world concept. The idea of literally splitting into multiple copies of himself with every quantum measurement seemed like a gigantic step backward. He simply could not take it seriously. Yet the relentless logic of Everett's mathematics began to gnaw at him. He tried to find a flaw in the reasoning, a crack in the foundation of the theory, but he couldn't. The Schrödinger equation was the bedrock of quantum mechanics, and Everett had done nothing more than follow its implications to their logical, albeit terrifying, conclusion. Slowly, painstakingly, DeWitt's skepticism transformed into advocacy. He began a correspondence with the now reclusive Everett, drawing him back, however briefly, into the world of theoretical physics he had abandoned. It was DeWitt who became the theory's champion, its most powerful and articulate evangelist. He saw what others had missed, that the theory's supposed weakness was actually its greatest strength. It didn't add complexity, it removed it. It dispensed with the messy, ill-defined collapse postulate and the arbitrary split between observer and observed. All it asked was that we believe the math. In 1970, DeWitt published an article in the widely read magazine Times Physics Today Times explaining the theory to a new generation of physicists. It was he who, in an effort to make the idea more vivid and accessible, coined the unforgettable name by which we know it today, the many worlds interpretation. The name itself was a stroke of genius. It was dramatic, evocative, and captured the breathtaking scale of the concept. With DeWitt as its champion, the theory was reborn. It was no longer an obscure footnote in a graduate thesis. It was a living, breathing contender, a radical alternative that demanded to be taken seriously. The seed that Everett had planted more than a decade earlier had finally begun to germinate. But it wasn't just DeWitt's advocacy that fueled this powerful resurgence. A new field of science was emerging, one that would find Everett's abandoned theory not just elegant but essential. That field was quantum cosmology. This is where the true power of many worlds began to reveal itself. Quantum cosmologists are concerned with the biggest questions imaginable, the origin and evolution of the entire universe. They seek to apply the laws of quantum mechanics, not just to atoms and particles, but to the cosmos itself. And in doing so, they ran headfirst into a profound, seemingly insurmountable roadblock presented by the Copenhagen interpretation. Remember, the Copenhagen view insists that a quantum system remains in a fuzzy superposition of all possible states, times, until times it is measured by a classical external observer. Only then does the wave function collapse into a single definite reality. But this raises a terrifying question. If the universe itself began as a quantum fluctuation and a singularity described by a universal wave function, then who was the observer? Who was there outside of the entire cosmos to measure the Big Bang and force its wave function to collapse into the specific universe we inhabit today? The Copenhagen interpretation requires an observer who is not part of the quantum system they are measuring. When the system times the entire universe, there is by definition nothing outside of it. The theory demands a divine spectator, a view from outside that simply cannot exist. It creates a logical paradox at the very moment of creation. The framework that works so well for describing laboratory experiments seemed to utterly break down when applied to the cosmos as a whole. Suddenly, Everett's many worlds interpretation looked less like a wild fantasy and more like a lifeline. In the many worlds view, there is no need for an external observer. There is no collapse. The universal wave function of the early universe simply evolved. Governed by the elegant, deterministic sweep of the Schrödinger equation, it branched. It branched into a universe where the fundamental constants were just right for stars and galaxies to form. It branched into another where they weren't. It branched into a cosmos with slightly more matter than antimatter, allowing our existence, and it branched into another where they annihilated each other into a sea of pure energy. Every single possibility encoded in that initial quantum state became a real physical universe, a separate world on its own cosmic trajectory. The theory provides a framework for a self-contained universe, one that needs no outside intervention, no magical collapse, and no privileged observer to bring it into being. The universe in this picture is the ultimate quantum computer, constantly and effortlessly exploring every possible outcome of every quantum event. For quantum cosmologists trying to build a consistent model of our cosmic origins, this wasn't just an elegant solution. It was, for many, the times-only times coherent solution. It transformed the observer from a necessary creator of reality into just another component of it, a branching pattern of quantum information like everything else. You, me, the planets, the stars, we are all just intricate structures, evolving times within times, the universal wave function, not external agents, forcing it to bend to our will. This incredible utility in cosmology revealed the deeper appeal that DeWitt had first recognized, a profound, almost aesthetic allure of mathematical purity. Physicists are often guided by a sense of beauty, by a belief that the fundamental laws of nature should be simple and elegant, and beneath its mind-bending implications, the many worlds interpretation is at its mathematical core astonishingly simple. It is the Copenhagen interpretation that is complicated, that is messy. The Copenhagen view takes the pristine, universally acclaimed Schrödinger equation, which describes the smooth, continuous evolution of the wave function, and then crudely bolts on a second, entirely separate process, the collapse. This collapse is violent, instantaneous, random, and irreversible. It's an times ad hoc, times addition, a patch put there for the sole purpose of making the math line up with our limited classical experience. There is no equation that governs it, no deeper principle from which it arises. It just happens. Everett's genius was to realize this patch wasn't necessary. He proposed that we simply remove it, that we trust the original, beautiful, unbroken mathematics of quantum mechanics. His theory introduces no new physics, no new equations or arbitrary constants. It is the most conservative approach possible. Its only requirement is that we have the courage to accept what the existing equations have been telling us all along, that all possibilities are equally real. The seeming complexity of infinite worlds arises not from complex laws, but from the repeated application of one supremely simple one. The charge that many worlds violates Occam's razor, DeWitt and others argued, was a complete misunderstanding. You don't apply the razor to the times outcomes times of a theory, you apply it to the theory's core times assumptions times, or postulates. Many worlds has only one postulate, the wave function evolving, according to the Schrödinger equation. Copenhagen has two, the wave function's evolution times, and times the collapse postulate. By this crucial metric, it is many worlds that is the simpler, more parsimonious, and more elegant theory. This potent combination, its necessity for a consistent cosmology, and its profound mathematical simplicity, fueled a slow but powerful revolution. Throughout the 1,970 seconds and 80 seconds, the theory gained traction among a new generation of physicists, including figures like David Deutsch, who would later build upon it to formulate the theory of the quantum computer. They were a generation less beholden to the authority of Bohr, more willing to explore the wilder frontiers of physics. They saw in many worlds not a philosophical nightmare, but a vision of a cosmos that was grander, more majestic, and more logically coherent than the old view it sought to replace. It explained the illusion of randomness in quantum mechanics, not as a fundamental feature of nature, but as a simple consequence of our own perspective. From inside a single branch, the other branches are invisible, and so the outcome of a quantum event appears random to us. But from the God's eye view of the entire multiverse, there is no randomness at all. There is only the serene, deterministic, and majestic unfolding of the universal wave function in all its infinite splendor. The idea began to seep out of the esoteric world of quantum cosmology and into the broader scientific consciousness. It offered tantalizing, if unprovable, answers to other deep questions. Why are the constants of nature so perfectly fine-tuned for life? Perhaps, in the infinite ensemble of universes, every possible combination of constants exists, and we naturally find ourselves in one of the few where conditions are right for us to exist and ask the question. It's a concept known as the anthropic principle, and it finds its most natural home within the framework of the multiverse. The lonely rejected theory of a disillusioned graduate student had, through a slow and arduous journey, finally found its voice. It had been rescued from obscurity and elevated into one of the most fiercely debated, compelling, and awe-inspiring ideas in all of science. But to truly accept it, to stand on the shores of one reality and believe in the infinite ocean of others, requires more than just an appreciation for elegant mathematics. It requires a fundamental shift in our understanding of what it means to be real, and it raises a new set of deeply troubling questions. If there are infinite versions of you, what does that do to the concept of your own identity? And most critically of all, is there any conceivable way we could ever peer through the veil to find even a shred of physical evidence for these other worlds that the theory so confidently predicts? The quest for that evidence would take physics on an even stranger journey into the very heart of what we thought we knew about reality itself. And so we arrive at a vision of reality as breathtaking as it is terrifying, a cosmos of infinite branches born from the quiet, simple rules of quantum mechanics, a theory that smooths away the jagged paradox of measurement, that banishes the ghost of collapse, and preserves the elegant, unbroken evolution of the universal wave function. It is in many ways a perfect solution, a pristine mathematical cathedral, built not of stone and glass, but of pure, unadulterated logic. Yet within this perfect structure a deep and unsettling echo resides. It is the echo of a question, the spectre of a doubt, that haunts the very foundations of this magnificent worldview. For the many worlds interpretation, in its quest for mathematical purity, asks you to pay a price so steep, so cosmically extravagant, that for many it borders on the absurd. To save the integrity of the equation, you must sacrifice the singularity of the world. And not just once, but an infinite number of times, every fraction of a second for every quantum event happening everywhere. This is the first great hurdle, the colossal stumbling block for skeptics and philosophers alike, the sheer profligate ontological cost. Occam's razor, the age-old principle that the simplest explanation is usually the best, seems not merely blunted by many worlds, but utterly shattered. The theory populates reality with a quantity of universes so far beyond astronomical as to render the term meaningless. Think about it. Not just when you make a momentous decision like accepting a job or choosing a partner. No, the splitting is far more mundane, far more constant. Every radioactive atom in the Earth's crust deciding whether to decay now or a moment from now, a split, a new universe born for each possibility. Every photon from the sun, striking a leaf, choosing to be absorbed or reflected, split. Two entire universes identical in every way except for the fate of that single quantum of light now sail away from each other in the grand expanse of Hilbert space. Every stray particle in the cosmic void interacting with another split. Every quantum computation in the heart of a distant star. Split, split, split. The number of parallel worlds created in the time it takes for you to draw a single breath defies any form of human comprehension. It is an infinity of infinities, a sea of branching realities that makes the number of stars in our own observable universe look like a single grain of sand. The theory demands that these other worlds are not mere mathematical fictions, not ghostly possibilities, but are every bit as real, as solid, as tangible as the world you are experiencing right now. Somewhere, a version of you exists who blinked a microsecond later than you just did. Another exists where the ambient noise in this room is infinitesimally different, and another, and another. This is what critics call a failure of quantitative parsimony. While many worlds may be simple in its axioms, just the Schrödinger equation and nothing more, it is wildly impossibly complex in its output. It posits a near infinite amount of unseen, unprovable, and unfathomably vast structure, all to explain the strange behavior of the microscopic. For many physicists, this is not an explanation. It is a cosmic sleight of hand, replacing one mystery, the measurement problem, with an even greater one, the mystery of an infinite, unobservable multiverse. It feels like burning down an entire forest just to roast a single marshmallow. Is the mathematical neatness of the theory truly worth the price of infinite, unprovable worlds? But even if you can swallow this staggering ontological cost, a deeper, more insidious problem awaits. It is a problem that strikes at the very heart of what makes quantum mechanics a predictive science. It is the problem of probability. For over a century, the engine of our quantum understanding has been the Born rule. It's a simple, almost mystical prescription that connects the mathematics of the wave function to the reality we observe. It tells us that the probability of finding a particle in a certain state is equal to the square of the amplitude of its wave function. This rule has been confirmed in countless experiments with breathtaking precision. It works. It is how we build lasers, design microchips, and understand the fusion furnace of the sun. It is the rock upon which all of quantum prediction is built, and in the many worlds interpretation, this rock crumbles into sand. The dilemma is as profound as it is simple. If every possible outcome of a quantum event actually happens in some branch of reality, then what does it mean to say that one outcome is more times probable times than another? Imagine a quantum coin flip an electron whose spin can be either up or down, with a 50/50 probability according to the Born rule. When you measure it, the universe splits. In one world you see up, in another an equally real version of you sees down. Both outcomes are guaranteed to occur. So where did the 50/50 probability go? If everything happens, the probability of any given outcome seems to be 100%. The theory in its deterministic perfection appears to erase the very concept of chance. Why then, when we perform these experiments thousands of times, do our results perfectly match the statistical predictions of the Born rule? Why do we experience a world governed by quantum odds when the underlying reality of many worlds insists that there are no odds at all, only certainty? This is the so-called preferred basis problem, or the measure problem, and it is arguably the most significant technical challenge facing the theory. It suggests that the Born rule, our gateway to quantum prediction, does not emerge naturally from the core axioms of many worlds. It has to be put back in by hand, an ad hoc assumption that undermines the theory's claim of supreme elegance. Proponents have wrestled with this for decades, proposing ingenious, if highly abstract, solutions. Perhaps probability arises from a form of self-locating uncertainty. You know that after the split there will be a version of you who saw heads and a version who saw tails. You just don't know which of those future descendants you are going to be. The probability in this view is not a measure of what times happen in the world, but rather a measure of your rational degree of belief, or perhaps your degree of caring about which future self you will become. Another approach attempts to derive the Born rule from decision theory, arguing that a rational agent living in a branching multiverse would have to place their bets according to the Born rule or face certain ruin. These arguments are subtle, complex, and far from universally accepted. For many, they feel like reverse engineering a justification for a result we already know to be true. They are attempts to recover the probabilistic world of our experience from a deterministic multiverse that seems to have no place for it. The pillar of probability so solid in the old quantum mechanics becomes tenuous and spectral here in the many worlds. And it is here in this fractured landscape of infinite copies and uncertain probabilities that the questions turn from the coldly physical to the deeply personal. For if the theory is true, what does it mean for times? Who are you in this endless branching tree of existence? The sense of a single, continuous, unique self, the bedrock of our identity, begins to dissolve into a dizzying hall of mirrors. You are not one person journeying through time. You are a pattern, a consciousness, constantly splitting and diverging into countless streams. There is a you that took that other job, a you that never met your partner, a you that turned left this morning instead of right. Each of these individuals shares your past, your memories, your very essence right up to the moment of divergence. Each feels with absolute certainty that they are the one true continuation of your consciousness. And yet their futures will be entirely different. This raises deeply unsettling questions. Are you responsible for the actions of your duplicates in other worlds? If one of them commits a heinous act, does that reflect on you? If another achieves a great discovery, do you share in that triumph? The very notion of a moral or existential narrative for your life becomes problematic. Your story isn't a single novel. It's an infinite library of choose-your-own-adventure books, and every single path is taken. Success and failure, wisdom and foolishness, kindness and cruelty, all of your potentials are realized somewhere. It makes your choices seem both monumentally significant, creating entire universes with each decision, and simultaneously weightless as every alternative is also playing out. Consider the ultimate divergence, a life or death situation. A game of quantum Russian roulette where a particle's spin determines whether a gun fires or clicks on an empty chamber. You play and the gun clicks. You feel a wave of relief. You survived. But in another branch, which is just as real, the gun fired. A version of you identical to you in every way, with your memories, your hopes, your fears, is now dead. Your survival in this branch does not erase the reality of your death in another. The loved ones in that universe are now grieving for a you that is gone forever. What does this do to our understanding of tragedy, of loss of consequence? In the grand accounting of the multiverse, no one is ever truly lost because a version of them always survives in some other branch. But that is of no comfort to the people in the branch where they are gone. This concept, known as quantum immortality, suggests that from your own subjective point of view, you will always find yourself in a branch where you survive, because you cannot experience the branches where you cease to exist. You would seem to yourself to be immortal, surviving any probabilistic threat, while watching those around you perish as they always would. It is a lonely, solipsistic, and deeply chilling vision of existence. This radical reimagining of the self has led some thinkers down an even stranger path to an offshoot of many worlds known as the many minds interpretation. Troubled by the idea of endlessly creating new physical universes, this theory proposes something perhaps even more bizarre. The physical universe, it suggests, never actually splits. There is only one universe existing in a permanent state of massive quantum superposition. All the possibilities, the live cat and the dead cat, the electron with spin up and spin down, are all physically coexisting in the same space at the same time. Instead of the times world time splitting, it is times consciousness times itself that fractures. For every possible outcome of a quantum measurement, a different thread of consciousness, a different mind branches off to perceive that outcome. The physical reality is a single, unified but blurry whole. Our perception is what carves it up into definite states, with each observer's mind splitting into an infinite number of successors, each experiencing a different, crisp, classical reality. This avoids the problem of creating infinite matter and energy out of nothing, but it does so at the cost of creating an infinite number of non-physical minds. It multiplies entities not in the world, but in the observer. It paints a picture of a single static quantum statue viewed by an infinite number of minds, each seeing it from a slightly different angle and believing their view to be the only one. Is this more or less extravagant than many worlds? It's a matter of philosophical taste. It swaps a physical multiverse for a mental one, a move that only deepens the sense of solipsism and decouples our conscious experience from a shared singular reality. It solves a physical puzzle by creating a metaphysical abyss, which brings us finally to the last great war, the objection that for most working scientists is the most damning of all. It is a simple, brutal question: where is the evidence? Science as a discipline is built on the foundation of testable predictions. A theory must be falsifiable. There must be some experiment, at least in principle, that could prove it wrong. If a theory cannot be tested against reality, it risks becoming something else entirely. It risks becoming metaphysics, a philosophy, a story, and many worlds, by its very nature, seems to stand behind an impenetrable veil. The other branches, the other universes, are causally disconnected from ours. The moment a split occurs, the different worlds can no longer interact or exchange information. They are, by definition, unobservable. We can never receive a signal from another branch. We can never peek across the divide to see the version of ourselves who made a different choice. The theory posits an infinite amount of reality that is forever beyond the reach of our telescopes, our microscopes, our most sensitive detectors. How then can we ever hope to prove it true, or more importantly, prove it false? Its critics argue that it is a theory of everything that explains nothing because it can accommodate any outcome. Whatever you observe, many worlds can simply say, yes, that happens in this branch without offering a testable reason times why times it happened here and not elsewhere. It is, they claim, the ultimate unfalsifiable hypothesis, a grand, elaborate, and mathematically beautiful story that has removed itself from the realm of empirical science. This is not entirely fair. Proponents argue that the theory times is times testable because it makes the same experimental predictions as standard quantum mechanics, just without the messy ad hoc collapse postulate. They claim its test is its elegance and logical consistency. Some have even proposed highly speculative borderline science fiction scenarios for testing it from complex analyses of the cosmic microwave background for signs of inter-universe bruising to the aforementioned ethically nightmarish quantum suicide experiment. But as of now, there is no practical agreed-upon test that could distinguish the many worlds reality from any other interpretation. And so we are left here at an impasse. We stand before a theory that may be the deepest, most accurate description of reality ever conceived by the human mind. A theory that flows directly from the mathematics we know to be true, a theory of stunning power and elegance. Yet it comes with a baggage of infinite ghosts, an army of unseen worlds, a fracturing of probability, a dissolution of the self, and it is protected from our prying questions by a shield of absolute untestable isolation. It presents us with a choice. Not a quantum choice that will split the universe, but a philosophical one. Do we accept this extravagant, unsettling, yet mathematically pure vision of the cosmos? Or do we reject it as a grand metaphysical fantasy and continue our search for a different answer, for a new interpretation that might finally bridge the gap between the quantum world and the one we call our own? The debate rages on in the hushed halls of physics departments and the pages of esoteric journals as we continue to grapple with the very nature of what is real. And so we stand at the precipice of an astonishing conclusion. We have followed Hugh Everett's logic to its ineluctable end, dismantling the paradox of Schrödinger's cat, not by forcing a choice, but by accepting every possibility. We have arrived at a cosmos of infinite branching timelines, a multiverse born not in the distant heavens, but in the quantum flutter of every atom every moment. It is a reality of staggering, almost terrifying elegance. One that solves the measurement problem with a single clean stroke, preserving the mathematical purity of the Schrödinger equation and restoring a sense of objective reality independent of any observer. But if we accept this, if we truly entertain the idea that countless versions of you are living out every conceivable outcome of every quantum event, a new, more profound question takes hold. It is no longer a question of mathematics, but of evidence. If these other worlds are real, separated from us by the thinnest of quantum veils, then where are they? How could we ever hope to glimpse these adjacent realities, these echoes of choices not made when the theory itself seems to erect an impenetrable wall between them? This is the grand challenge for the modern proponents of many worlds. It is one thing to propose a beautiful theory, but quite another to find its signature in the fabric of existence. Direct communication is by definition impossible. A branch once split is causally disconnected. You cannot pick up a phone and call another version of yourself. Yet physicists armed with new theoretical tools and a deeper understanding of the quantum realm have begun a search not for a gateway, but for a shadow. They are hunting for the faintest of gravitational whispers, the most subtle of quantum statistical anomalies that might betray the presence of this silent, invisible crowd of parallel worlds pressing in on our own. The search begins where our two greatest theories of reality collide, in a spectacular, unresolved conflict. On one side, we have Einstein's general relativity, the majestic theory of the large. It describes a smooth, flowing geometric spacetime, a cosmic fabric warped by mass and energy. On the other, we have quantum mechanics, the chaotic and probabilistic theory of the small, which insists that at the tiniest scales, reality is granular, fuzzy, and fundamentally uncertain. For decades, the quest for a theory of quantum gravity has been the holy grail of physics, a single mathematical framework to unite these two warring ideas and write the unified score for the symphony of existence. And it is here, in this violent clash of titans, that the many worlds interpretation makes a dramatic entrance. Some physicists now believe that the very structure of the multiverse might be the key to unlocking this ultimate theory. Think of our universe, our single branch, not as an isolated entity, but as one leaf on an infinite tree. String theory and its successor M theory already predict a landscape of perhaps 10 to the 500 possible universes, each with its own physical laws, its own fundamental constants. The many worlds interpretation populates this landscape. It provides the engine of creation, the branching mechanism that brings these potential universes into being. In this breathtaking vision, the quantum foam at the bottom of reality is not just a chaotic soup of virtual particles winking in and out of existence within our own cosmos. It is the very soil from which new branches, new entire universes constantly sprout. The immense gravitational forces at a black hole's singularity, or the unfathomable energies of the Big Bang, might not just be endpoints or beginnings, but junctions, cosmic gateways where the branching of worlds becomes so extreme, so violent, that the fundamental character of reality itself can shift. In this context, physicists are searching for gravitational anomalies. If another branch universe, a world nearly identical to our own, were to interact with ours on a quantum level, it wouldn't create a portal. It would be far more subtle. It might manifest as a tiny, inexplicable gravitational pull, a slight deviation in the motion of a hypersensitive detector that cannot be accounted for by any matter within our own branch. Experiments are being designed to look for these phantom forces to see if the cosmic ledger balances perfectly, or if there is a minute gravitational discrepancy, a ghost in the machine hinting at the mass of worlds we cannot see. Furthermore, the many worlds interpretation offers a startling, if controversial, solution to one of the biggest mysteries in cosmology, the cosmological constant. This is the energy of empty space itself, the dark energy that is causing the expansion of our universe to accelerate. Our best theories predict a value for this energy that is 120 orders of magnitude larger than what we actually observe. It is the single worst prediction in the history of science. But in a near-infinite multiverse, this problem can dissolve. If every possible value for the cosmological constant exists across the vast spread of branches, then it is no surprise that we find ourselves in a universe with a value perfectly tuned for the formation of stars, galaxies, and life. Most worlds would be inhospitable, either recollapsing in an instant or expanding so violently that not a single atom could form. We, by necessity, find ourselves on a branch where the conditions are just right. This is a form of the anthropic principle, but empowered by the MWI, it becomes a statement not of luck, but of statistical inevitability. We are the survivors living in a life-sustaining oasis within a cosmic desert of failed realities, and the fine-tuning of our cosmos is merely a selection effect. We are here to observe it because in the other branches there is no one to ask the question. Our existence itself in a universe so exquisitely balanced could be the most profound piece of circumstantial evidence for the multiverse. Beyond the cosmic scale, the echoes of many worlds may be reverberating right now in our most advanced technology. The nascent field of quantum computing is in many ways a direct manipulation of the very branching that Everett described. A classical computer bit is either a 0 or a 1. It lives in a world of certainty. But a quantum bit or qubit exists in a superposition of both 0 and 1 simultaneously. When a quantum computer with hundreds of these qubits performs a calculation, it explores a vast number of possibilities at the same time. Its computational power grows exponentially, dwarfing any classical computer imaginable. But where is this phenomenal computation actually happening? From the perspective of the many worlds interpretation, the answer is both simple and mind-boggling. The quantum computer isn't just a clever box of hardware, it is a portal to the multiverse. When it begins its calculation, it splits reality. In one branch, the qubit is a 0. In an adjacent branch, it is a 1. A machine with hundreds of qubits is performing its calculations across billions upon billions of parallel universes simultaneously. It is leveraging the colossal parallel processing power of reality itself. Each branch explores a different computational path, and at the end of the calculation, these branches are carefully brought back together to interfere with the incorrect answers, cancelling each other out, and the correct answer being amplified. When we use a quantum computer, we may not just be engineering silicon and lasers. We may be conducting the architecture of reality, orchestrating a symphony of computation across a sliver of the multiverse. The staggering power of these machines could be the first tangible technological proof that these other worlds are not just a mathematical fiction, but a utilizable physical resource. This perspective also casts one of quantum mechanics' oldest and strangest features in a completely new light: entanglement. This is the spooky action at a distance that so troubled Einstein, where two particles can be linked in such a way that measuring a property of one instantly influences the other, no matter how far apart they are. In the Copenhagen view, this is a deep and unresolved mystery. But within the many worlds framework, the spookiness vanishes. When you create an entangled pair of particles, say with opposite spins, you are not creating a mysterious long-distance connection. You are linking the future versions of yourself across different branches of the multiverse. Imagine you measure one particle and find its spin is up. In that instant, the universe branches. In your branch, the particle is up. You know with absolute certainty that your colleague trillions of miles away on your same branch will measure the other particle and find its spin is down. There is no faster than light signal. There is no spooky communication. It's simply a matter of correlation. On another branch, you measured the particle as down, and you know with equal certainty that the version of your colleague on that other branch will measure up. Entanglement is not a mystical tether between particles. It is the mundane logical consistency of the universal wave function, a thread of correlation that runs through the branches, connecting the different versions of you to the different outcomes you observe. It transforms from an unnerving paradox into a simple statement of cosmic bookkeeping, and it is here in this re-evaluation of observation, measurement, and existence that we arrive at the most extreme, the most personal, and by far the most disturbing implication of the many worlds interpretation. It is a thought experiment that takes Everett's logic to its absolute chilling conclusion, forcing us to confront what it truly means to be a conscious observer in a constantly splitting reality. This is the theory of quantum immortality. To be clear, this is not a mystical belief in an afterlife. It is a stark, rigorous, and terrifying deduction from the core principles of the theory. The thought experiment is often called quantum suicide. Imagine a device is set up pointing at your head. It is connected to a quantum measurement apparatus, say one that measures the spin of an electron. If the spin is measured as up, the device does nothing. It clicks, and you survive. The experiment is repeated 1 second later. If the spin is measured as down, the device instantly triggers and you are killed. According to the standard laws of probability, with a 50/50 chance each second, your survival is extraordinarily unlikely. Within seconds, the odds of your continued existence drop to near zero. From the perspective of an outside observer watching this horrifying experiment, you would be dead almost instantly. They would see the spin measured as down on one of the first few tries, and that would be the end. But what do times you times experience? According to the many worlds interpretation, every time the measurement is made, the universe splits. In one branch, the spin is down and you are killed. Your consciousness, your subjective experience ceases in that branch. In the other branch, the spin is up, the device clicks, and you survive. You are alive and conscious, waiting for the next measurement 1 second later. From your first-person perspective, you can only times ever experience the outcomes in which you survive. The branches in which you die are by definition inaccessible to your conscious mind. For you, the experiment continues, the device clicks, you survive, another second passes, the universe splits again, in one new branch you die, in the other you live. And your thread of consciousness continues hopping from your point of view from one surviving branch to the next. From your subjective viewpoint, the device will always click. The spin will always be measured as up. You will witness an impossible statistical miracle surviving against infinitesimal odds, second after second, minute after minute, forever. You are immortal. Not because your body is indestructible, but because your consciousness can only ever follow the unbroken chain of cause and effect that leads to its own continuation. To the outside world, you are long gone. But from the inside, you live on the sole inheritor of a timeline that had to exist by the laws of quantum mechanics, a timeline where the coin toss just kept landing on heads eternally. This isn't a promise of eternal life, it's a potential curse. You would be destined to watch everyone you know age and die, to survive every accident, every disease, every calamity, your consciousness funneled into the ever slimmer, ever more improbable branches of reality, where survival was the only remaining option. This thought experiment, while impossible to perform, forces us to the core of what it means to be you. If MWI is correct, then you are not a single entity. Your identity is not a single precious thread, but a massively braided rope of experience, constantly fraying into new strands, each one a valid and real continuation of your life. The person you are right now is just one of countless descendants of the person you were a moment ago. Causality, the comforting notion that one event leads to a single next event, is revealed to be a local illusion, a narrative we tell ourselves within the confines of a single branch. The true structure of reality is not a line but a labyrinth, a sprawling, ever-expanding tree of possibility where every path is taken. What then is a choice? What is a life? MWI suggests that our reality is not a story with a single plot, but an infinite library containing every possible version of that story, all being written at once. We do not choose a path so much as we experience one of them. Every act of creation, every decision, every moment of quantum uncertainty enriches this cosmic library, adding another volume, another variation on the theme. We are all collectively authoring the book of everything. This reshapes our very definition of existence. It suggests that the universe we see, the life we lead, is but one facet of a far grander, far more complex and unimaginably vast crystalline structure of reality. And the great unanswered question that echoes down every one of its infinite hallways is no longer whether these other worlds are real, but who in this endless fractal of selves are we? And so we are left here at the precipice of an idea, so vast it threatens to dissolve our very sense of self. We have journeyed from a simple, baffling pattern of light and shadow on a detector screen, from a single particle seemingly in two places at once, a ghostly superposition that defied all classical intuition. This was the foundational crack in our understanding of reality, a fissure that physicists have spent a century trying to mend. Some patched it with mathematical formalism, declaring the mystery solved by simply stating that observation forces a choice. They gave us the Copenhagen interpretation, a pragmatic but deeply unsatisfying pact with the bizarre. It demanded we accept a universe that plays by one set of rules when we aren't looking, and another entirely different set when we are. A quantum world of limitless potential that inexplicably collapses into a single mundane actuality the moment it is witnessed. This act of collapse, this sudden violent reduction of possibilities, has always been the ghost in the machine. It is a rule added to the pristine mathematics of quantum mechanics, a seam stitched into the fabric of reality that shows the hand of the tailor. It works, it allows us to build lasers and computers, but it feels arbitrary, an appendage to an otherwise beautiful theory. It was into this intellectual void that Hugh Everett III stepped armed, not with a new experiment, but with a fearless logical blade. He looked at the Schrödinger equation, the undisputed mathematical heart of the quantum realm, and saw its truth. He saw that it never not once predicted any collapse. It described a smooth, continuous, elegant evolution of possibilities, a wave of potential spreading ever outward. His audacious proposal was to simply trust the math, to take the theory at its word without adding any ad hoc rules to make it conform to our limited classical experience. If the equation shows the particle going through both slits, then in some fundamental way it does. If it shows the cat as both alive times and times dead, then it is. The collapse, Everett argued, isn't a physical event happening out there in the universe. It is a subjective illusion, happening only within the consciousness of the observer. The moment you make a measurement, the moment you open the box and look at the cat, reality doesn't shrink. You don't force the universe to choose. Instead, the universe and you along with it splits. One version of you in one branch of existence sees a living cat and continues on in a world where that outcome is fact. Simultaneously, another version of you, absolutely real and just as convinced of their own uniqueness, sees a dead cat. They continue on in their own universe, a universe that has now diverged forever inaccessible. This is the many worlds interpretation in its stark, terrifying, and magnificent glory. It is not a theory of what might be, but a declaration of what, according to the unadulterated laws of physics, times must times be. It is an idea born not from a desire for science fiction, but from a profound commitment to logical and mathematical consistency. It mends the fissure in reality, not by patching it over, but by revealing that the fissure was in fact a gateway. MWI's most fervent adherents are drawn to its sheer elegance, its intellectual purity. It rids quantum mechanics of its awkward duality, its special pleading for the act of observation. In the world of Everett, there is no magical boundary between the quantum and the classical. Everything from a single electron to a swirling galaxy, from a curious physicist to the equipment she uses, is a quantum system. All are governed by the same universal law, the Schrödinger equation, unfolding in perfect deterministic harmony. The seeming randomness of our world, the quantum coin toss that lands on heads or tails, is an illusion of perspective. From a godlike vantage point outside the multiverse, there is no chance at all. Every possible outcome of every quantum event simply times happens asterisk. The wave function of the entire multiverse, a colossal, intricate entity, never collapses. It just evolves, branching endlessly, spawning new worlds with every quantum interaction, every single moment. This is a staggering thought, an almost unbearable burden of infinities. But for a physicist dedicated to Occam's razor, the principle that the simplest explanation is usually the best, it is sublime. You trade one perplexing arbitrary rule, the collapse of the wave function, for an infinity of unseen universes. It seems like a bad bargain, a wild escalation, and yet in the language of mathematics and theoretical physics, it is a simplification. It creates a cleaner, more powerful, more comprehensive picture of reality's fundamental operations. It restores a form of classical determinism to the universe, not for our world, but for the multiverse as a whole. There is no spooky action at a distance, only local interactions branching the timeline. There is no paradox of Schrödinger's cat, only a branching of realities, one for each outcome. The theory takes our deepest questions about why nature behaves so strangely and answers with a calm, revolutionary retort. It doesn't. It is we who only perceive a tiny sliver of a much grander, perfectly logical whole. We are riders on a single branching stream, mistaking our limited journey for the entirety of the river. This elegance is the source of its power and its enduring appeal. It offers a potential path out of the philosophical labyrinth that has trapped physics for a century. It suggests that the universe is not absurd. It is merely vast beyond our capacity to perceive. It is a vision of cosmic architecture so grand that our entire history, our loves, our wars, our discoveries are but one pattern, one thread in an infinite and ever-growing tapestry. Of course, the towering objection remains a question that echoes in every critique of Everett's vision. Where is the proof? How can we call this science if its central prediction, the existence of these other worlds, is fundamentally untestable? You cannot visit these other realities. You cannot communicate with your other selves. The moment of the split is by its very nature a perfect and irreversible parting of the ways. The laws of quantum mechanics themselves erect an impenetrable wall between these parallel streams of history. This is a profound challenge, and it is the reason why the many worlds interpretation remains an interpretation and not an accepted fact. Science, after all, is built upon the bedrock of empirical, falsifiable evidence. A theory, no matter how beautiful or mathematically consistent, must eventually face the crucible of experiment. It must make predictions about the world we can see and measure predictions that differ from its rivals. For now, MWI shares all its experimental predictions with the standard Copenhagen interpretation. They are in our single universe observationally identical, and so, for many, the choice between them becomes a matter of philosophical taste, not scientific necessity. Do you prefer a single strange universe where reality is conjured into being by observation, or do you prefer an infinity of perfectly normal universes that are forever hidden from view? It is a choice between a strange process and a strange ontology. But to dismiss many worlds as mere speculation, as unfalsifiable metaphysics, might be premature. The history of science is filled with ideas that were once considered beyond the reach of experiment. The existence of atoms was debated for millennia before we developed the tools to finally see their influence. The curvature of space-time proposed by Einstein was a mathematical abstraction until a solar eclipse proved him right. The frontiers of testability are not fixed. They are constantly expanding, pushed outward by human ingenuity and technological advance. The question then is not whether we can prove many worlds today, but whether we can imagine a pathway to proving it tomorrow. What future discoveries, what new windows into the cosmos might finally allow us to glimpse the shadow of a neighboring world? The search for an answer is already underway, not in a single dedicated experiment, but in the subtle background of several cutting-edge fields. It is a search that requires us to think differently, to look for the indirect whispers of the multiverse in the data we collect. One of the most promising and perhaps surprising arenas for this search is inside the quantum computers, now being built in labs around the world. These are not just faster versions of the machine on your desk, they are fundamentally new kinds of devices designed to operate on the very edge of quantum reality. A classical computer bit is a simple switch, either a 0 or a 1. A quantum bit, or qubit, however, can exist in a superposition. It can be both 0 times and times 1 at the same time. By linking many of these qubits together, a quantum computer can explore a vast number of potential solutions to a problem simultaneously. Its computational power grows exponentially with each added qubit, reaching scales that are impossible for any conceivable classical computer. But where does this incredible power come from? One of the pioneers of quantum computing, David Deutsch, is a firm believer in the many worlds interpretation. He argues that the very act of a quantum computation is experimental evidence for the multiverse. When a quantum computer performs a calculation, he suggests it is not just happening in our universe. The machine is effectively outsourcing parts of its computation to a vast number of parallel universes. It is leveraging the resources of its otherworldly counterparts, running calculations on different branches of reality simultaneously. The final answer we receive in our lab is the result of this massive parallel processing effort, a collaboration across worlds. From this perspective, the impossible speed of a quantum computer is a shadow of the multiverse at work. We aren't directly seeing the other worlds, but we are harnessing their collective power. If Deutsch is right, then every time a quantum algorithm solves a problem once thought unsolvable, we are receiving a message. A message that says, our universe is not alone, that we are part of a much larger computational engine. It is not definitive proof, but it is a tantalizing hint, a piece of circumstantial evidence that resonates with the core claims of Everett's theory. It transforms the multiverse from a passive, unseeable backdrop into an active computational resource, a cosmic hard drive we are just learning to access. The quest for a fully functional large-scale quantum computer is therefore not just a quest for faster processing. It may also be a quest for the first tangible artifact of the multiverse. Beyond the laboratory, out in the unimaginable vastness of space, another search is unfolding. Cosmologists are scrutinizing the most ancient light in the universe, the cosmic microwave background. This faint residual glow from the Big Bang is a snapshot of the cosmos in its infancy, a baby picture of reality. It is remarkably uniform, but it contains tiny, almost imperceptible fluctuations in temperature. These fluctuations are the seeds of all structure, the primordial lumps that would eventually grow into the galaxies, stars, and planets we see today. Most of these variations are well explained by our standard model of cosmology, known as inflation. This theory posits that the early universe underwent a period of hyper-accelerated expansion, stretching from a subatomic point to cosmic scales in a fraction of a second. But some versions of inflation, called eternal inflation, suggest this process never truly stops. Our Big Bang was not a unique event, but merely one bubble of space-time nucleating in a much larger, eternally inflating multiverse. Other bubbles, other universes would be constantly forming, each potentially with different physical laws and constants. If this picture is correct, is it possible that our universe, our bubble, once collided with another? Could such a cataclysmic primordial event have left a detectable scar on our cosmos? Theorists suggest it might appear as a specific anomalous pattern in the cosmic microwave background. A kind of cosmic bruise, a circular cold spot or hot spot, distinct from the random noise of the early universe. Searches for such a signature are ongoing. So far, no unambiguous evidence has been found, and many promising signals have turned out to be instrumental errors or statistical flukes. But the search continues, pushing the limits of our observational power. Every new satellite, every more sensitive telescope, gives us a clearer picture of that ancient light. We are sifting through the afterglow of our own creation, looking for a faint, ghostly fingerprint. The fingerprint of a neighbour, a sign that we were not born into an empty void, but into a crowded cosmic foam of countless other worlds. A positive discovery would be the single greatest revelation in the history of science. It would confirm that the multiverse is real and that the foundations of our reality are far grander and stranger than we ever dared to imagine. Yet perhaps the final answer will not come from a computer or a telescope, but from the mind of a single theorist. Physics is currently in a state of profound anticipation, searching for a theory of everything. A single, unified mathematical framework that can seamlessly weave together Einstein's general relativity, the law of the very large, with the bizarre rules of quantum mechanics, the law of the very small. This is the holy grail of modern physics, a quest that has consumed the greatest minds for generations. When this theory is finally found, if it is ever found, it will represent our deepest understanding of reality's architecture. It will provide the ultimate rulebook for how existence works, and within that rulebook, the status of the many worlds interpretation may finally be resolved. The theory of everything might show that a branching, splitting multiverse is a mathematical necessity. Or it might reveal a deeper mechanism for the collapse of the wave function, vindicating the Copenhagen view. It could even unveil a third possibility, a picture of reality so new and unexpected that it makes all our current interpretations seem quaint. We do not know what this ultimate theory will look like. But we know that the questions it must answer about the nature of time, the origin of the universe, the structure of reality itself, are intrinsically linked to the puzzle of many worlds. The answer to whether we live in a multiverse may not be something we find, but something we derive. A truth that emerges not from observation, but from the flawless, inescapable logic of the final equation. And so we are brought back full circle to ourselves, to you. If the many worlds interpretation is true, then this journey we have taken together is not just an intellectual exercise, it is a description of your own personal reality. Right now, as you watch this, countless quantum events are happening in your body and your surroundings. The decay of a radioactive atom, the path of a photon, the firing of a neuron in your brain. With each event, the universe branches. An unimaginably vast number of other yous are being created this very second. Each one is identical to you in every way, sharing your memories, your thoughts, your feelings up until this instant. But now their paths have diverged. One of them just saw a dust mote catch the light in a slightly different way. Another decided to get up and leave the room. Another is living in a world where you made a different choice this morning, a different choice last year, a different choice a decade ago. Every road not taken, every path abandoned, every opportunity missed or seized, all of it was real. It all happened. There is a version of you who pursued that different career, who moved to that other city, who said the thing you wish you'd said. There is a version who succeeded beyond your wildest dreams, and a version who failed spectacularly. There is a you who is happy, a you who is grieving, a you who is just being born, and a you who is taking your last breath. You are not a single person, but a colossal branching tree of selves spreading through the infinite dimensions of possibility. This realization is profoundly humbling and deeply empowering. It means that no single life, no single timeline carries the full weight of your potential. Your identity is not contained within this one body, this one sequence of events. It is a symphony of all possible experiences, a chorus of infinite voices, each one singing its own unique story. Does this diminish the importance of the choices you make here in this world, or does it elevate them? Knowing that every decision you make creates a new real world, a new history for a version of yourself, lends a certain gravity to every moment. It transforms life from a single finite story into an act of continuous cosmic creation. We stand at the shore of an ocean of possibilities, able to perceive only a single drop. The many worlds interpretation is a map, a theoretical chart that suggests the ocean is real. It tells us that just beyond the horizon of our senses lies a multiverse of staggering scope, a place where all stories are true, where all paths are walked. It remains an unproven and perhaps unprovable idea, a beautiful, elegant, and deeply unsettling piece of mathematics, but its value may not lie in whether it is ultimately proven true. Its value lies in its power to expand our imagination, to shatter our comfortable assumptions about a singular reality. It forces us to confront the profound weirdness that lies at the heart of our existence. It encourages us to ask the biggest questions of all. What is the fundamental nature of the reality we inhabit? Is what we see all there is? Or are we part of something infinitely grander, a branching, endless story written across countless worlds? The answer still waits for us, hidden somewhere in Exa's Deimos, the quantum foam in the light from the beginning of time, in the next great leap of the human mind. And until we find it, we are left to wonder and to dream. Dream of the infinite other selves living out the infinite other lives, just a quantum vibration away from our own.